Today we are doing a critical deep dive, and it's on a topic that really, it separates the pros from the novices in the procedure room, setting up and operating the electrosurgery unit, or ESU. And just so everyone knows where we're coming from, our entire analysis today is based on this fantastic YouTube video from Dr. G.S. Raju. It's called HCC 1472 Lesson 16C Electrosurgery Unit Setup.
Exactly. And our mission here is to go beyond just, plugging it in. We're using the Irby machine as our main example to really understand the settings.
Right.
The goal is fluency, knowing the physics, the circuit, and how to change those cut and coag parameters on the fly during a procedure.
And we'll be covering both monopolar and bipolar systems. The focus is on getting this knowledge down fast, understanding that current path, and this is key, how to troubleshoot when things go wrong under pressure.
So let's start with the foundation, the monopolar setup. It's all about creating a complete circuit, and the first rule is just. It's about safety and visibility.
Visibility. Rule number one, you're saying the ESU has to be right there in front where everyone can see it.
Absolutely. It cannot be off in a corner somewhere. The endoscopist, the assistant, they need to clearly see those parameters on the screen before any current is delivered.
It sounds a lot like a nurse double-checking a medication before giving it.
It's the exact same principle. It's a critical safety step. You visually confirm the settings, the program, the power level every single time. It's your pre-flight check.
Okay, so we've got the unit in the right spot, we press the power button, and let's say we select the hot snare program. Now we start connecting things.
Exactly. Now we build the circuit. And for a monopolar system, you need two key things to complete that loop.
Okay.
First, the monopolar electrode, that's the active part that delivers current to the snare. And second, the dispersive pad. You might hear it called the neutral electrode.
And that's the part that returns the current.
That's the part that safely returns the current back to the generator.
So where does that pad go? I mean, placing it correctly seems pretty important.
It's crucial. For endoscopy, you want it on a large muscular area, like the thigh or the back. The goal is to make the path for the electricity as short and direct as possible, and you need maximum skin contact.
Okay, so the pad's on the patient, the electrode is connected to the machine. What's next?
With all the hardware connected, you press the green button right next to the monopolar outlet. That kind of arms the system. It tells the machine you're ready to go.
And the actual delivery of the current comes down to the foot pedal.
All down to the foot pedal.
Huh.
And the color coding here is universal. Yellow pedal is cut.
Right.
Blue pedal is coagulation.
So why are they different? I mean, they both use electricity, but one cuts tissue and the other stops bleeding. How does that work?
It's all about the waveform. The yellow pedal, the cut current, uses a continuous, high-frequency, low-voltage current. It's constant.
So it's always on when you press it.
Exactly. And that continuous energy is so concentrated at the tip of the snare that it literally vaporizes the water in the cells. That's the cut.
Wow, okay, and the blue pedal?
The blue pedal, coagulation, that's different. It's an intermittent pulsed current. It's also high voltage, but lower frequency.
So it's on, off really fast.
Right, and those little pauses give the tissue a moment to cool down. So instead of vaporizing, you get this slower, broader heating that desiccates the tissue and stops the bleeding.
That makes so much sense. So the assistant's job is just to make sure that pedal is right where the endoscopist can comfortably use it.
Yep. So to put it all together one last time, that current path is generator, out through the monopolar electrode to the snare, through the tissue.
Where the resistance creates the heat.
That's right. Then back through the patient to the dispersive pad, and then the neutral electrode cable takes it back to the generator. A full, complete, uninterrupted loop.
Okay, that brings us to the high-stakes scenario, part 2. You're in a procedure, the endoscopist steps on the yellow pedal to cut a polyp, and nothing, just a silent click.
Right. This is where your training really kicks in. The first thing you have to do is look at the machine immediately.
And what are we looking for?
You're looking at the neutral electrode segment on the ESU screen. If that circuit is broken, the machine's going to scream at you with two distinct brown icons.
2 brown icons, so that's the big warning sign. Stop, something is fundamentally wrong.
Exactly. And when you see them, you have to run a mental checklist, and you have to do it fast.
Okay, so what's step 1 on that troubleshooting list?
You start with the most common and honestly the most embarrassing mistake.
Watches.
Is the monopolar outlet even hooked up properly? I mean, is that cable fully seated in the socket on the machine? It sounds basic, but it happens.
It's always the simple things. Okay, so we check the connection at the machine. It's solid. What's step 2?
You just follow the current. Is the connection to the snare good? Then step 3, check the dispersive pad on the patient. Is it fully adhered? A partially attached pad is incredibly dangerous. It can cause a burn,
A catastrophic event.
a total disaster. And then, finally, step 4 is checking the other end of that dispersive pad's cable. Is it plugged in securely to the machine?
So, 4 points. Machine outlet, snore connection, pad on patient, and pad cable at the machine.
You check those 4 points systematically, you'll find the problem in seconds. You have to treat those brown icons like a 5-second countdown.
And the all clear signal.
The brown icons disappear, and the screen shows a nice lightest green-blue color, as Dr. Raju puts it. That's your green light. The circuit is complete and safe.
And how does this compare to a bipolar setup? Is the troubleshooting that intense?
No, not at all. Bipolar is way simpler. The current path is just between the 2 tips of the forceps.
Oh, so you don't need the dispersive pad.
Exactly. No dispersive pad needed. The circuit is contained in the instrument itself. You just select the program, plug it in, and you're ready, and you only use the blue pedal for coagulation.
Okay, that's clear. So we've nailed the circuit and troubleshooting. Let's get into the deep dive on the parameters. This is where the real skill comes in. We're looking at the Urbe machine, yellow panel for cut, blue for coag.
Right. And for something like a snare polypectomy, we're almost always going to be using a blended mode called Endocut.
And the machine has 2 types, Endocut Q and Endocut I. I know Q is for snares and I is for things like a needle knife, but why? What's the functional difference?
Well, Endocut Q is specifically designed for the larger surface area of a snare wire. The Q mode balances that cut and coag cycle perfectly for removing a polyp without causing a perforation.
Okay.
Endocut I, on the other hand, is for very fine, precise incisions, like with a sphincterotomy. It has a different energy profile for controlled, deep penetration.
Let's break down the 3 big parameters inside Endocut Q. The first one is effect.
Right, effect. It's a scale from 1 to 4, and it controls the intensity of the coagulation that happens in between the cutting pulses.
Okay, so if I set the effect to 1, what am I telling the machine to do?
Effect 1 means you want almost no coagulation. It's a pure cut. It's very fast, but you have a much higher risk of bleeding.
So it's fast but dangerous.
In vascular tissue, yes. Which is why the standard setting is usually effect 3.
Why is 3 the sweet spot?
Effect 3 gives you a great balance. It gives enough of a pause between the cut bursts for a good, solid coagulation to happen. It's the best mix of speed and safety for a typical polyp.
And effect 4 would be too much.
Yeah. Effect 4 is pretty intense coagulation. You risk charring the tissue, which can actually delay healing, so it's all about that trade-off.
Speed versus bleeding risk versus thermal injury.
Got it.
Okay, parameter 2, cut duration.
Duration, also on a scale from 1 to 4, controls how long each individual cutting pulse lasts.
And the recommendation is to start at duration 1. Why is that?
Duration 1 gives you these very short, quick bursts of cutting. It's like you're feathering the current. It gives the endoscopist incredible control to see how the tissue is reacting and stop if they need to.
So you would only increase the duration for what? Tougher tissue.
Exactly. If you're trying to get through some thick scar tissue or something, you might bump it up to a 2 or a 3. It gives you more power to cut through that resistance in a single go.
That makes sense. And finally, parameter 3, cut interval. This is about the timing between the cycles.
Precisely. This is the rest period. The time delay between the end of one cut cog cycle and the start of the next one.
And we found some specific numbers for this in the source material, which were fascinating.
They really were. With a duration of 1, the interval can be as fast as 400 milliseconds. So you're getting a new cut cycle, bang, bang, bang.
But if you max out the interval setting...
Then the delay can be a full second. A new cut cycle only happens every 1 second.
And why would you want that long 1-second delay?
For maximum safety. If you're really worried about bleeding from a very vascular polyp, that long interval gives the tissue the most time to cool and allows for the most robust coagulation to take hold. The standard is usually interval 3, again, right in that middle ground.
Okay, so we understand the parameters. If the endoscopist says drop the effect from 3 to 2, how do you physically do that?
It's super simple. You just press the button right next to the word effect on the screen, and that lets you use the up and down arrow buttons to change the number. The key is being able to do it instantly without thinking.
Okay, let's quickly touch on the other coagulation modes before we wrap up.
Of course. The machine has other options like soft, force, and spray coag. And as we've discussed before, they all do different things. Soft is deep and slow, force is a bit faster, and spray is for wide, superficial bleeding.
So if the procedure changes, say you've removed the polyp, but now there's a small bleeder you need to zap with force coag, how do you switch programs?
You'd hit the Guides for Program button That lets you exit Endocut Q, takes you back to the main menu, and then you can select a totally new program, like Force Coag. Then you just engage that new program.
And the big takeaway here, which Dr. Raju really hammers home, is that you have to know this machine cold.
Oh, absolutely. His recommendation is to literally play with the machine during your downtime.
You cannot afford to be figuring out the buttons when a patient is bleeding on the table.
No way.
Yeah.
That fluency, that muscle memory, where the doctor says, lower the effect and your hand is already moving, that's what makes a great assistant. It lets the doctor stay focused on the patient.
All right, this deep dive has been incredibly useful. Let's just review the absolute key takeaways. First, the non-negotiable importance of visibility of that ESU screen.
Critical for safety.
Second, knowing that 2 brown icons means you have a circuit fault and you need to troubleshoot immediately. And third, really understanding the difference between effect, duration, and interval.
We really went from just plugging it in to understanding the huge clinical difference between a 400 millisecond interval and a 1-second interval. That's where precision comes from.
It certainly is, and we learn that the yellow pedal's cutting current is continuous and low voltage, while the blue pedal's coagulation current is pulsed and high voltage. So here's a final thought to leave you with. If the coagulation current is high voltage, why is it less likely to vaporize tissue than the low voltage cutting current? What else about that waveform's shape and frequency prevents it from creating that instant superficial cut and instead achieves that deep, broad coagulation? That's the principle you should explore next.